In this section, we will discuss how the key measurements of the optical flow meter are used to determine the multiphase flow rates. We will start with two-phase liquid-liquid flows and first demonstrate the importance of the speed of sound measurement. What is shown in this plot is the speed of sound variation for a fluid mixture, in this case oil and water, where the amount of water in the total liquid, which we call water cut, is progressively increased from 0% on the left to 100% on the right. So at 0% water cut, which means 100% oil phase, one of the boundary conditions of this curve is the oil speed of sound, which is about 1000 meters per second for this example. Of course, that number changes depending on the type of the oil, whether it is light oil, heavy oil, or depending on the temperature and pressure. On the right, at 100% water cut, we have the second boundary condition, which is the speed of sound of water, right around 1500 meters per second. Now, this curve is uniquely determined for a well-mixed fluid mixture. And it is based on Wood's equation, which was developed about 100 years ago by Albert Wood. The implication of this curve is that if a flow meter is capable of measuring speed of sound, then the intersection of this measurement and this curve will give us the phase fraction information directly, in this case, the water cut. Knowing the water cut will allow us to determine the phase flow rates using this simple set of equations. Here, Q total is the total volumetric flow rate, and that information comes from the velocity measurement and the cross-sectional area of the flow meter. Once we obtain the water cut, the WLR, then it is easy to calculate the oil and water phase flow rates. Now, I mentioned that this curve is uniquely determined, but that is for a given pressure and temperature measurement at a specific time. At time T2, we may have a slightly different pressure and temperature, which also triggers a change in this curve as well, mostly because the oil speed of sound is a strong function of pressure and temperature. So at every data point, these measurements are made, a new curve is drawn, a new water cut is determined, and new phase flow rates are calculated. So these are all in the flow computer, and everything is done automatically. Another observation on this curve is that it is very well behaved. What I mean with well behaved is for a given speed of sound measurement, there is a unique water cut value. So there is a one-to-one relation. And this is a typical feature of the liquid-liquid mixtures. Now, we will see on the next slide for gas-liquid mixtures that this may not be a standard behavior. So let's talk about the performance. The total flow rate uncertainty of this two-phase system is plus minus 5%. And also the phase flow rate uncertainties are about the same, plus minus 5%. But that is for the initial installation of the flow meter. Once the flow meter is in the well, the performance can be improved at the steady state production of the well. At some point, the test separator measurements on the surface become available. And when they are available, it is possible to use those measurements and optimize the boundary conditions of this curve. Now, initially, sometimes it is difficult to determine these boundary conditions before the production begins. But we have a method to optimize these boundary conditions once those measurements from the test separator are available. And the performance goes up to plus minus 1% at that point. That is an excellent performance for a multi-phase flow meter. Now let's move on to two-phase gas-liquid mixtures. And again, we are seeing the speed of sound variation for a gas-oil mixture this time. And the oil amount, in this case, we will actually indicate as liquid volume fraction for the oil. For the liquid is the oil. So the oil volume fraction will be changed from 0% to 100%. And again, the phase flow rate calculations are similar. We make a speed of sound measurement, and that will correspond to a specific HL, liquid volume fraction. And we can use that information to calculate the gas and oil phase flow rates. Now, I mentioned that for gas-liquid mixtures, the curve is a challenging curve. And this curve is actually using the same equation. It is still the Woods equation. However, the reason for this challenging shape is the gas phase. So why is it challenging? It is challenging because for some speed of sound measurements, we may end up with two solutions rather than one, as in the liquid case. So let's present an example. Here we have an example speed of sound measurement of 400 meters per second, this horizontal dashed line. So it intersects the Woods curve at two locations. This is location number 1, and here location number 2. So these are two valid solutions. Fortunately, those two solutions correspond to very different flow conditions. The first solution is actually a gas-rich flow. The liquid volume fraction is around 5%, which means gas volume fraction is 95%. So this must belong to a gas producer. The second solution is the oil-rich point, oil-rich solution. So this must come from an oil producer. So how do I choose between these two solutions? Well, the answer is simple. We have a prior knowledge of the well. So the application, we know the application, whether it is gas producer or oil producers. So because we know that, we can actually set the correct solution configuration in the flow computer and obtain the correct liquid volume fraction and the liquid phase flow rates. So in terms of performance, again, the total flow rate and phase flow rate performances are about the same. The uncertainties are plus minus 5%. Sometimes for some regions of this curve, it may actually go up to 10%, plus minus 10%. But as long as we stay in these high gas or high liquid regions, this uncertainty number is valid. So let's move on to three-phase flow measurement. And for that, I will be using this plot. At initial look, it looks like this is a complex plot, but once explained, I believe it will be all clear. Speed of sound versus density. And what we have here is a unique shape it looks like Sinbad's scimitar. But for us, it is the three-phase solution domain, or sometimes we call it the three-phase solution envelope. Now, what is interesting about this solution envelope is that the corners of this solution region corresponds to single-phase gas, single-phase oil, and single-phase water. In addition, the boundaries of this region are the two-phase solutions. This is the oil-water two-phase solution, the well-behaved curve that we have talked about 2 slides ago. This is the oil and gas curve in the previous slide, the challenging curve. And this is also the gas-water curve. We haven't talked about this, but this is essentially the same as the gas-oil one. It's a gas-liquid curve. So the only difference for these two-phase solutions is that instead of speed of sound versus density in the previous slides, we have plotted speed of sound versus water cut or liquid volume fraction. So essentially, they are the same. So let's continue to explain this this region, this solution domain, because we have more curves here. The dashed purple curves, they are the water cut counters. Those water cut counters intersect the oil-water curve at here 20% water cut, 40%, 60%, and 80%. The frequency of these counters is by choice. We can have 1% frequency if we want. The yellow dashed lines, those are the liquid volume fraction counters. So here, this is 80%, sorry, 90% liquid and 10% gas. This is 80% liquid, 20% gas, and so on. So why are these important? Because the water cut and the liquid volume fractions are the phase fractions. They define the three-phase point. If I know them, I would completely solve my three-phase flow. Now, interestingly, this point here, there is a three-phase solution point. This is an example point that I selected. Now that actually there is a water cut counter that goes through this point, and there is a liquid volume fraction counter that goes through this point here. Now, interestingly, I can actually reach this point through external measurements by measuring the speed of sound and the density. So we have a point, and that point has a relation with 4 quantities: speed of sound, density, water cut, and liquid volume fraction. Now, how do we define a point? A point is the intersection of either 2 lines, right here, speed of sound and density, or it could be the intersection point of 2 curves, the water cut and the liquid volume fraction, or it could even be the intersection of a line and a curve. So it doesn't matter how I get 2 of these 4 quantities, but as long as I measure 2 of these 4 quantities, that means I have solved the three-phase flow completely. I can obtain the remaining 2 quantities from that point. So let's say if I have a flow meter measuring the speed of sound and density, now I can completely solve this point. I can calculate the phase fractions through the, there is a relation of these quantities. There is an equation. So I can find the water cut and the liquid volume fraction if I measure these. Or if I have a flow meter which can only make the speed of sound measurement, but if I can add a water cut measurement to that, now I can also get that intersection point. So in earlier sections, when I talk about the three-phase measurement for our flow meter, I mentioned that we use two different methods to measure three-phase flow. One method was to measure density along with the speed of sound measurement, and the density measurement was through the use of the secondary PT gauge. And or for the second method, I can use a water cut meter and determine the water cut value along with the speed of sound measurement. Now, on the next slides, we are going to go deeper on these two methods. So now let's talk about method number first. In this first method, the optical flow meter and the PT gauge number 2 is used. Now, the idea here again is to predict the density. Now, how do I do that? I have a PT gauge integrated to the flow meter. Now I'm going to be using my secondary PT gauge, and I will be measuring a differential pressure between these 2 points. Now, this secondary PT gauge is preferably installed with a vertical distance to the flow meter. Now, the reason I would like to have that vertical separation is that this differential pressure, which is pushing the fluid from point 1 to point 2, is being opposed by 2 different forces, frictional force and the hydrostatic pressure force. Now, having a vertical distance means that guarantees that I have a hydrostatic pressure, which is basically the weight of the fluid between these 2 points. Now, having 2 separate points, that also guarantees that I have a frictional pressure as well. So that differential pressure is used to beat the frictional loss and the hydrostatic pressure, the weight of the fluid. Now, where is the density? The density term is in these 2 terms. Both friction and the hydrostatic terms include the density term. Now, obviously, they have more complex expressions, but I have here the conceptual equation. The differential pressure between 2 points basically is used to beat the frictional force and the hydrostatic pressure. So now these 2 terms may have different order of magnitudes, especially if the secondary PT gauge is close to the flow meter. Now, in that case, the frictional term is going to be very small. So we are going to be relying on the hydrostatic pressure measurement. And that is why the vertical separation is important. Now, I sometimes get this question whether it is possible to use the flow meter in a horizontal configuration. If the well is completely horizontal, whether or not we can actually make a 3-phase flow measurement. The reason for that question is the second term, the hydrostatic term, is 0, because if there is no vertical separation, then that term is 0. The answer to that question is yes, we can. It is possible to do 3-phase measurements even in the horizontal configuration, as long as this frictional term is large enough. Now, if this is large enough, that means that I may have the resolution to predict the density. Now, what does that mean? Having a larger frictional loss, well, that means that the secondary PT gauge needs to be installed far away from the flow meter. Now, how far, that will be determined on a case-by-case basis. For a given application, we will have to look at the data from the application and come up with the correct distance to determine the correct separation of the PT gauge number 2. So let's move on to another feature here in this solution domain. If you notice, as we go to left, as we move to left in this solution domain, all these water cut counters converge to a single one. So it becomes almost impossible to distinguish the oil and water phases within the liquid phase. And this solution almost becomes a two-phase solution. It becomes like a curve rather than a region. So that indicates that we must have some limitations regarding this method number 1. So we have done extensive flow loop testing with this method, and we have determined that as long as the gas volumetric fraction is at or below 30%, we are staying within this region here, this high resolution region, and we are able to measure the three-phase flow. So above 30%, now it becomes fuzzy, and it is very difficult to make that measurement. Now, that 30% looks like a modest number, but for a downhole measurement, it is a very realistic number, because in most cases, the flow meter, the location of the flow meter is deep in the well, and the pressure at that location is usually around the bubble point pressure. There is a lot of flow meter installations where the pressure was above the bubble point, so there was no free gas. But even if it is below the bubble point, even if there is gas in the flow, that 30% seems to be a realistic number. Now, there may be some applications, obviously, where this 30% GVF is not satisfied. So for those applications, we recommend method number 2, which I will describe here. In method number 2, we use the optical flow meter and a water cut meter. In this case, red eye. Red eye is our water cut meter. Now, just to make the distinction between the two methods, in method number 1, the PT gauge is a downhole equipment. In this case, method number 2, the water cut meter is not a downhole equipment because it has a probe inside, so it obstructs the flow. For that reason, it is not installed downhole. It is either at the wellhead on the platform or at the subsea level. So we have a subsea version, and the picture here refers to the subsea version of this water cut meter. Now, in terms of solution, again, instead of density, we are measuring speed of sound and the water cut. So we are actually reaching our three-phase flow point. And once we do that, once we get that point, we can also calculate the density and liquid volume fraction. So one more point that we need to make here, because the red eye water cut meter is either at the subsea level or at the platform level, then there is, in most cases, there is going to be gas in the flow stream. So the good thing is that the water cut technology, the measurement technology, is not affected by the presence of gas. So the solution, the three-phase solution, is possible up to 100% GVF with this method number 2. So let me go a little deeper on this method number 2 on the next slide. So recapping the measurements, the optical flow meter provides the velocity measurement, speed of sound measurement, and pressure and temperature measurements. And the water cut meter provides the water cut measurement. Now, the operating principle of the red-eye water cut meter is based on the absorption spectroscopy of the phases in the near infrared wavelength region. So this is a plot showing absorption versus the wavelength in the infrared, near infrared wavelength region. And as you see, we have different fluids, oil A, oil B, and water. So we have also other fluids as well. So as you notice, we have very different absorption profiles for water. And that actually is the reason why the water cut meter is so efficient to make the water cut measurement without being affected by the presence of gas or even the chemistry of the fluid. So what I would recommend on this water cut meter, I'm not going to go into more detail, but there is a very nice animation available on YouTube, which describes the measurement technology in detail. So these two products are available, commercially available, and they provide robust measurements. However, the integrated system has not been installed in the field yet. The integration is underway, and we have done flow loop testing using these two products and post-processed the data. And we had excellent results. And now I will briefly mention these results. First, at the component level, we have the velocity measurement and the speed of sound measurement from the optical flow meter. Those measurements are within plus minus 5% of the reference systems. And we have a water cut measurement from the water cut meter. And again, the measurements is within plus minus 5%. So let's see how these component level raw measurements are used in the phase flow rates in the system level measurements. And here are those measurements. First, the total flow rates here, and gas, oil, and water flow rates are shown. Now, the total flow rates are within plus minus 5%, and gas, oil, and water rates are plus minus 10%. We had some outliers, as you can notice. Now, we had some issues related to the facility. For some test points, we had foaming developed in the test section, and there were some acquisition time issues, mainly due to human errors. So we could have actually obtained better uncertainties, but this was really a post-processing of these two robust systems. We know that this provides a very viable solution for a multi-phase flow measurements up to 100% GVF. This is very important because these two systems, the integrated system, we believe provides a better cost structure compared to available technologies from other companies, especially in the subsea multi-phase flow meter market. The subsea multi-phase flow meters are extremely expensive. So that's why we believe that we will have a better cost structure, and we will at least match the performance of the available options from the market. And on top of that, we have some advantages which come with this integrated system. What are those advantages? Well, this integrated system can be used for a wide range of applications. subsea, offshore, or land. It is based on a non-nuclear technology. In most surface and subsea multiphase flow meters, manufacturers use gamma densitometers. They are devices based on nuclear technologies. And whenever the word nuclear is used, we have a lot of regulatory requirements, spatial training requirements, liability concerns. So this integrated system eliminates all these issues related to nuclear technologies. As I mentioned in earlier sections, the system provides high flow range, high turn-down ratios, at least 25. The optical flow meter is capable of measuring the flow in both directions. And for that reason, it can be used in injector applications or producer applications, or it could be first initially producer and then could be converted to injector, which we will also see in a case history in the later sections. It can also detect cross flow with this feature. It is possible to obtain the zonal contribution rates in a multi-zone well. We can place multiple flow meters between zones and obtain the contribution rates from different zones. The water cut meter, the red-eye water cut meter, is very sensitive to water, and it can detect the onset of water very efficiently. So it's a water onset detection tool. In terms of gas, the optical flow meter in its measurement is also very sensitive to the presence of gas. Anytime a minuscule amount of gas is introduced to the flow stream, there is a dramatic decrease in the speed of sound measurement. So that actually tells us the presence of gas. So having a water onset detection and gas detection technologies, a client, an operator, is able to optimize the production of the well. Let's assume that there is a multi-zone well and there are inflow control valves between the zones. So if the water or gas is detected from the measurements, then using those ICVs, inflow control valves, in an efficient manner, it is possible to block or reduce the unwanted fluids for that zone. In terms of form factor and weight, the optical flow meter is a part of the production tubing. It is inside the well, so there is no contribution to form factor or weight at the subsea level. And the only component is the red eye. And as you have seen in the previous picture, it's a very lightweight and it has a very small footprint compared to very large subsea structures. Both technologies, red eye and optical flow meter, are solid tolerant. The presence of solids have little or no effect on the accuracy of their measurements. So we believe that the integrated system provides better economics and also increased functionality. Once the optical flow meter is in the well, that means the fiber optic infrastructure is already available. That also helps us to enable other fiber-based technologies such as distributed temperature sensing, DTS, or distributed acoustic sensing, DAS. So it is possible to expand the functionality of the system using those other technologies as well when required. So now let me congratulate you for completing this longest section of the training on multiphase flow measurements.